Welcome everybody to our lecture today, which is going to be on properties of curl and divergence. Now, there are many properties of curl and divergence that can be shown, but we're only going to mention a few of the ones that we're going to need later on in our Calculus 3 course. So in order to do this, let's set up our notation. So I'm going to think of a vector field F with component functions, and these are functions, P in the first component, Q in the second component, and R in the third component. So this is our vector field on R3. And the other vector field that plays a key role in this is the gradient, which you can think of as the partial with respect to x, the partial with respect to y in the second component, and the partial with respect to z in the third component. So by this notation, for example, I mean the partial of whatever with respect to x. So that's a shorthand commonly used. That makes it just a little quicker to write things. Okay, and so if you take a scalar function, that is, say, f maps R3 into R, that's what you mean by a scalar function, gives you back a real number, then the gradient of f just means f sub x, f sub y, f sub z. We know that from way back when, earlier in the class, okay? But now when we take a vector field and we want to do different operations with the gradient, since this is also a vector, we can't just say the gradient of capital F. It doesn't have a meaning. So you learned that in the earlier videos in the module that, how to define some important quantities. So let's remember those. Number one is the curl of our vector field F. And I like this notation better for the curl because it tells you exactly what to do. You take the cross product of the gradient vector with the vector field F. And when you do that, if you write everything out, which I am not going to do the whole cross product thing, I'll just tell you the results. You get R sub y minus Q sub z in the ith component. You get P sub z minus R sub x in the jth component. And in the kth component, you get Q sub x minus P sub y. Okay. All right, so that's the curl. And the divergence of F, which you can write in this way, but I like it better written as the dot product because it tells you exactly what to do. So you take the dot product of the grade of grad, the vector grad, with the vector field F, and you get F sub x plus F sub y plus F sub z. Okay. And that's the dot product always gives you a scalar, and the cross product always gives you a vector. So this makes sense in terms of what we know way back from the beginning of the class. Okay. So what are some of the important properties? So let's say property one. Suppose F maps R3 or some subset of R3 would work equally well into R. So we have a scalar valued function and F has continuous second partials. Then the curl of the gradient of F equals 0. Okay. And actually that's really easy to show because the why? Because when you take the curl of the gradient of F, Well, here's the definition of the gradient of f. And now we want to take the curl. So r is the third component, q is the second component, and p is the first component. So I'm taking f sub y, f sub y sub z. So again, let me grab a different color. Now I'm thinking in this calculation down here of this one as R, this one as Q, and this one as P, and then I'm using the definition of curl to write this down, okay? So I take R sub Y, so that's F sub, that's R sub Y is F sub Z sub Y, but that's F sub Y sub Z by Clairaut's theorem because the partials are continuous, okay? And then I have to subtract, now I just keep going in the same manner, minus Q sub Z, which is F sub Y sub Z, times I. So clearly that first term, first component of this curl is 0. And now what about the second component? So P sub Z is F sub X sub Z minus R sub X, but R sub X is F sub X sub F sub Z sub X, which is the same thing as F sub X sub Z because the second partials are continuous. Clearly that's 0. And now what about the last component? The last component is Q sub X, so that is F sub Y X minus P sub Y, which is F sub X Y, which is the same thing as Fy X. So this is 0, okay? All right, so that's the 0 vector. So it's trivial, you just check it, it's true. So if you take, and the way we say that is, in words, we say the curl of a gradient is 0. The curl of a gradient is the 0. And when I say 0, it's a vector because this is I should have written a vector notation here, but 0, it's pretty unambiguous. Okay, anyway, we'll fix that. Okay, all right. So that's one property. All right, now what about another property? Well, even before, okay, so property 2. If capital F is conservative, then the curl of F equals 0. Okay. Now, why is that true? Again, I'm doing the proofs because they're simple and it makes sense to you. I'm not going to ask you for the proofs, but things should make sense. F conservative means F equals gradient of F. F equals gradient of F for some scalar function F, okay? All right, and so F is equal to a gradient. And as long as the partial derivatives are continuous, so if P, Q, and R are continuously differentiable, that is the components of the vector field F, then this is equal to the curl of the gradient of the little f. And these little f's like this are called potentials, right? That little f is a potential for capital F. We know that already. And by the previous result, that's equal to 0. Okay, so by property, this is by property 1. Okay, so a conservative vector field always has curl 0. Okay. All right. And well, let me mention a theorem that's true, but is beyond the scope of this course to prove, at least at this point. I mean, we could do this at the end of the class, but it's unlikely we'll have a lot of time left. So let me just call it a theorem. The theorem says basically the converse of this is true. So suppose F is a vector field on R3. And suppose its component function are continuously differentiable. Okay, I abbreviate a lot. Okay, so it's continuously differentiable. If the curl of F equals 0, then F is conservative. Okay, so if you look at vector fields with continuous second part, whose component functions are continuously differentiable, then the curl being 0 is equivalent to the vector field being conservative. Okay, that's what the property 2 plus this theorem tells you. Okay, but the proof again of the theorem is too hard for us at this point. We don't have enough tools to do that. Okay. What's another property of curl and divergence that we're going to want to use? Let me switch to some properties of divergence. So let's say this is property 3. So again, our F, let's let F be the vector field PQR, and suppose PQ and R are continuously, are twice continuously differentiable. I need. Then the divergence of the curl is 0. Okay, and now this really is 0 because you're taking a dot product, so that's a number. Okay, not a vector 0, it's a number 0. Okay, all right, so let's see why that's true. Now, I'm going to need more space than the bottom of that page, so let's come up here. Let me do it this way. Okay, so let's figure out why that is true. Okay, so let's see. We want to take the divergence of the curl of F. Okay, so that means I want to take the partial with respect to X of, and looking back at our definition that we had before, that's R sub Y minus Q sub X. I'm sorry, Q sub Z. Okay, so you take the first component of the gradient vector, which is this, and the first component of this vector. Okay, and now you add to that you apply the second component from here, so that's the partial with respect to Y, and I take the second component from the curl, which was T sub Z minus R sub X. And then the third component, same thing. So I take the partial with respect to Z and apply that to Q sub X minus P sub Y. Okay. All right, so now let's write that out. So when I take this, this will give me RYX minus QZX plus PZY minus RXY plus qxz minus pyz. Okay, and now we remember that when all the partial derivatives are, when the second partials are all continuous, they're equal. So this is the same as that. The ryx is the same as the rxy. The qxz is the same as the qzx. And so you get 0. So again, it's absolutely trivial to show that the divergence of a curl is 0. And let's remember that in words as well, because sometimes it's easier to remember the words. So the divergence of a curl of a vector field is 0. Okay, so the last thing I want to mention in this section is the Laplace operator, okay? Because that's an important operator. It comes up all over the place in all kinds of applications. In differential equations, which arise in engineering and physics and biomedical engineering and just everywhere. If you're going to do any kind of serious science, you're going to run into a Laplace operator. Okay, so what do we mean by that? What I mean is I'm going to take, so I think of f as a scalar function with continuous second partials. And what I mean by, and let me look at, I define the Laplacian or Laplace operator okay, acting on f as, a mathematician writes it as delta f. A physicist will write it as del squared f, but they mean the same thing. In a way, this is a bit more informative because the definition is you take the dot product of the gradient with the gradient of the scalar function. So you take the gradient of the scalar function and you dot it with the grad vector. So what does that mean? This is take the dot product of fx, fy, fz. So that means fxx plus fyy plus fzz. So that's what the Laplacian of f is. I am more trained as a mathematician than any other kind of science, although I do mathematical physics. So I will use the usual mathematician notation for it, the delta, okay? Okay, so the Laplacian arises all over the place in applications in mathematics, in physics, in engineering, in all sorts of equations. For example, Laplace's equation, or Laplacian, appears in what's known as the heat equation. And so that's where this also describes any kind of diffusive processes or mixing of chemicals is modeled using the heat equation and variants of it with other terms. So I'm writing down the most basic version. The wave equation, which talks about propagation of waves. In this case, the way I wrote it, 3 dimensions. This equation by itself is called Laplace's equation. And for mathematicians, solutions of Laplace's equations are called harmonic functions, but also things that obey Coulomb's law satisfy an equation like this. So it just comes up all over the place. And if you do any kind of applied science at a serious level, you will run into the Laplacian operator. Okay, let me also mention that I wrote it down as a three-dimensional operator, but suppose you had a function, a scalar function f from Rn into R. Then how do you define del on Rn? Well, del is just the partial with respect to the first variable. Continue until you get to the partial with respect to the nth variable. If I wrote down the gradient of f, and f was a function in Rn, that would mean f sub x1, the partial of f with respect to x1, and you keep going until you get to the partial of f with respect to xn. And so the Laplacian of f would mean the same definition. And so what does that give you? That gives you fx1 x1 plus fx2 x2. And you keep going until you get to fxn xn. So the Laplacian in any dimension is the sum of the pure second partials. Okay. What do I mean by pure second partials? There's no mixed ones. It's x1, x1, x2, x2, fxn, xn, and so on. So it's the sum of the pure second partials in any dimension. Okay. So can you define the Laplacian, or can you make sense out of the Laplacian for a vector field? So again, let's go back to F, our vector field with component functions P, Q, and R. And now we're going to stick to 3 dimensions. I mentioned the n dimensions. And most everything we do in this class can be generalized to n dimensions. Okay, so what do we mean when we say the Laplacian of a vector field? And the book will likes to write it like this. So how do you define the Laplacian of a vector field? Because a vector field is different than a function, so this really means something different. It's not quite clear, but here's how we define it. We take the Laplacian of P, the Laplacian of Q, and the Laplacian of R. Okay. So what do you mean by the Laplacian of a vector field? You mean the vector field with each component being the Laplacian of the original vector field. So if I'm going to take the Laplacian of f, what that means is take the vector whose components are the Laplacian of each of the component functions of f. Okay. Okay. And basically, we will see all of this again when we talk about Green's theorem, which is in the next few lectures coming up in the course. Okay, so that's it for today. Bye.